Hello, my name is Samuel Lane. I'm from the University of Kansas, and I'm excited to talk to you about some of my recent work with my collaborators, Li Huang, Ian Lewis, and Jin Liu. The title of the talk is Electroweak Restoration into LHC and Beyond, the VH channel. And you can find our papers published in PRD, and I have the archive number listed in case you're interested in seeing it. And I hope everyone is enjoying the WIN conference so far, and look forward to hopefully talking to you guys during the panel discussion. So let's begin. First, let's go over what I'm going to talk about. So first I'll do some introduction and theory, and then I'll talk about parton level results, and then I'll talk about the actual results, so the full detector level simulation and the signal strength, and then I'll cover some statistics, and we'll talk about chi-square versus KL divergence. So without further ado, let's begin. So introduction and theory. So introduction. So we know the standard model is successful, but what about dark matter, the matter asymmetry in the universe? There's dark energy. There's all kinds of stuff that's not explained by the standard model. So there are a lot of strategies to learn more, but basically most of them come down to doing a direct search or looking for deviations from the standard model. And since the electroweak symmetry breaking is a critical component of the standard model, we propose that being able to measure it and measure it well is highly important to making sure we understand the standard model and hopefully maybe one day find some new physics. So yeah, so let's go over the theory. So we're all familiar with the Higgs potential, and when the Higgs acquires a vacuum expectation value, basically rolls this ball down the hill of the potential, and through the kinetic terms you end up with W and Z masses, and so this ends up breaking the electroweak symmetry of the standard model and gives everything its mass. So we're all pretty familiar with this. So let's talk about the electroweak restored phase, which is to say that we fix the electroweak couplings of G and G prime, and then we take the limit as VEV goes to 0, and so the Higgs no longer has a mass. And what this does is it means the W and Z no longer has a VEV, so the Higgs no longer has a mass too, and the W and Z also are massless, and the fermions are all massless, and really you should be thinking about the Se2L WIs rather than W and Z, and you should be thinking about the Higgs as a doublet rather than a scalar. Okay, so we've kind of covered the theory, so let's talk about what do I mean by measuring this electroweak restoration. So it basically comes down to Goldstone boson equivalence, and the idea is that the diagram on the left is with an H and a longitudinal Z coming out, and the diagram on the right is with an H and a G0, so the Goldstone mode. And the main point of the Goldstone boson equivalence is to say that the amplitudes converge in the high energy limit. And so to show you that, I've written down the amplitude for the ZLH and at the top and the G0H at the bottom. And you can see that in the order S expansion of the ZLH, it's the same as the G0H, which is to say that the longitudinal mode is basically the same as the Goldstone in the high energy limit. Okay, so that's the Goldstone boson equivalence. And basically we want to go about measuring this convergence. So let's talk about the parton level. So you can look at the helicity dependence for WH and ZH. So I'm showing the ratio of the cross-section of WH production for a particular polarization, so say longitudinal or transverse, over the total. And so what you can see for both WH and ZH, this is versus PT of the Higgs, you can see that in large PT, it's basically all longitudinal, which means that the cross-section itself in the high PT region already selects the particular amplitudes that we're interested in. And so we don't have to worry about separating polarizations as long as we're looking at PTs that are large. And so this is not the case if we were to say look at W and D, where you could look at similar Goldstone boson equivalence theorems. But the problem is that these are transverse dominated. And so if you want to be able to measure this convergence of the Goldstone boson equivalence, then you need to actually disentangle the polarizations. And this is a tricky problem that we are currently working on, and hopefully we'll have results soon. So, but anyway, so in this talk, we'll just focus on VH, so WH and ZH. Okay. Anyway, But so you can take your WH and ZH for either 14 or 27 TeV, depending on if you're interested in high Lumi or high energy LHC, and you can compute a signal strength. So this is to say we compute the ratio of the standard model VH cross section over the Electroweak restored Goldstone H cross section. Now this is slightly different than the normal Goldstone boson equivalence, which would hold in the standard model. This is to say we're computing the signal strength to an Electroweak restored model. And as you can see, the mu approaches 1, which is to say that the convergence is generally expected to be good for both 14 and 27, and it happens, I don't know, to 80% after 450, 400 GeV or so. So let's go ahead and move on. So this is kind of what we're going about to propose a plan to measure. So let's do that. So let's talk about the simulation that we plan to do, or that we did. So what we did is we considered 3 decay channels. So we looked at ZH goes to L plus L minus BB bar, WH goes to L nu BB bar, and ZH goes to nu BB bar. And we treat the simulated data basically as an experiment, and we want to compare this with the Electroweak restored expectation. And so we can do that. We can generate all our data with lots of different backgrounds. So we use MadGraph, Pythia, Delphi's chain to generate this standard model data, or this experimental data, if that's what you want to call it. So here is our events after our deep neural net. So we use a DNN to separate signal and background. And you can see we have quite a few number of events for the WV, top, W plus JJ, missing lepton, and the signal. And the signal here is the WH, 1 lepton. And put our loss function down here at the bottom if that's something that interests you. These are for the 2-jet and 3-jet final states at high energy LHC. And yeah, you can see that on the right, we can, the far right of the plot, you can see that the PTH is, or the signal grows above the background. And even on the left plot, even though it's not above the background, you can still disentangle it statistically. Yeah. So anyway, we can go about simulating this and treating this as our expected signal. And basically we have to unfold back to the 2-to-2 process, but that's not something that's too difficult. We kept track of the parton level information, so the truth level, and created an efficiency matrix to do so. The experimentalists, I think, have a more sophisticated way to do this, but we were just trying to be as close to experiment as we can. So let's go ahead and look at the results of the signal strength. So this is the 1 lepton case. So again, this is the ratio of the standard model VH cross section of the Electroweak restored Goldstone H. And on the left is 1 lepton for 14 TeV. The darker lines are the 2-jet, and the lighter lines are 3-jet. You can see the 2-jet tends to do quite a bit better. But even in the 1 lepton case at high Lumi LHC, it's maybe only order 100% accurate, I would say, even in the 2-jet. And then for 27 TeV, for the 2-jet, it's maybe 10% accurate. Or the uncertainties are about 10%, I should say, not that it's accurate. Anyway, but that's to say we could confirm it to that level. So we can repeat this process for the 2 lepton channel, the 0 lepton channel, and then combine all the results. So that's what we did. So here's the signal strength combined. So we can combine the results for both the 2-jet and the 3-jet, and then all of the 2 lepton, 1 lepton, and 0 lepton channels. And here's the signal strength versus PTH. On the left is for high Lumi LHC with full 3 inverse Atabarns data. And we can see we get to about 40% error. And these are the 68% confidence levels that I'm showing. Didn't say that on the last slide, but they were the same. And on the right, we have the high energy LHC, and the errors are at about 6%. And we've, I think, added statistical or systematic errors in quadrature. I think it was like 5% or something. I can't remember exactly what we added, but it was something similar to that. You can find the exact details in our paper. And so let's move on. So this is the signal strength. So we've shown how we would measure the signal strength, but let's talk about some statistics and how we would try to confirm our hypothesis that the Electroweak symmetry is restored at high energy. So let's start with the delta chi-square, because it's the easiest thing to do and often the most straightforward. So we can compute a delta chi-squared using logs of the ratios of Poisson distributions for different numbers of bends. And you can see on the left that when you just have the first bend, the chi-squared is quite large. And this is because the difference between the expectation of the Electroweak Goldstone and the standard model, WH or ZH, is quite large, but the uncertainty is very small because there's a large number of events in those first few bends. And as we can see, the chi-squared increases as we include more bends. And that's to say that our hypothesis of the Electroweak restored phase, or Electroweak restored cross-section, is gets better as you increase in PT, which is exactly like we would expect. But you could argue that while your chi-squared is getting smaller, your errors are getting worse, and so there's maybe some devious nature in this chi-squared. Maybe it's not telling the whole story. And so we wanted to go one step further. And so we looked at something called a KL divergence, which is to basically take ratios of likelihood distributions for one hypothesis versus the other. And it's similar to chi-squared in that small KL implies agreement with the hypothesis. But we expect the KL, and we expect the KL to decrease as we include more PT bends, but it's a little more robust than the chi-squared. And so what we want to do is we want to plot this just like we did before. And as we can see, the KL increases as we include more PT bends, and that it gets very small at the high PT bends. And that's to say that the hypothesis is in good agreement with the data, which our data here is the standard model stuff we generated through backgraph, which is to say that, we would agree that the standard model or that the Electroweak symmetry is restored at the high PT or the high energy, which is exactly what we set out to prove. So yeah, so with that, I think I'll just quickly wrap up. So we've shown the capabilities of high Lumi LHC and high energy LHC in observing the Goldstone boson equivalence theory and Electroweak restoration. We find for PTH greater than 400 GeV, the DH and the VH distributions agree at about 80%. And KL divergence shows that two hypotheses agree at high energy. And the high Lumi can confirm Electroweak restoration with about a 40% error, and high energy can confirm it within like 6% error, which is quite good. And with that, I thank you. And I hope to see you at the panel discussion if you have any questions. Thanks.